Yeah, sweet. Hey everyone, my name is Jinen. I'm a first year PhD student. I am doing research in optimization theory and intrinsic interpretability. Today I'm going to be talking about an incredible paper. It's the name of the paper is Average Gradient Outer Product as a Mechanism for Deep Neural Collapse. A lot of words, but we'll break it down step by step. If anyone has any questions along the way, please interrupt me and ask, and that will make things super or much more easier than if we save questions to the end. I'm very happy for this to be more of a discussion. Most of the stuff that I usually present, I feel like I have a good grip on, and this one is not like the others. I have some parts of it that I'm fairly confident on, but in case there are things that I don't know, I have the papers, so we can just go through them and figure out what exactly is the details. Alright, cool. So this is actually an amalgamation of 3 papers. There is this one, which is basically connecting these two distinct things, the average gradient outer product and deep neural collapse. So we will also talk about both of those things separately, what they are, why it is important. Before that, obviously, we'll get started with some amount of intuition and why this is exciting. Finally, we can cover the intricate connection between both of these two things that seem different, at least on the surface. Alright, so background and intuition. We can start with a very simple SVM. How many of you are familiar with SVM? Can I get a show of hands? Somewhat, so. Okay. So the basic setup, right, for SVM is that I have this 2D data, and I want to determine the sort of line of best fit that can classify the blue balls and the green balls, right? Anything that is below this red line is a green ball. Anything that is above this red line is a blue ball. And the main idea here is that I can have many lines that kind of perfectly separate this training data from this, or like the green balls from the blue balls, but how do I know which one is the correct line, so to speak? And the idea is basically that I want to maximize the margins between the two sort of extremum or 2 points that are closest to one another. So we have, for example, over here circles and x's, which is a cheaper way of drawing it. I basically take the point that is closest to the line, to a line that I draw, and I measure the distance from here and the distance from here. I sum this up, and this sum, so m sub 1, m sub 2, basically becomes my margin, and the goal is to basically maximize this margin. So if I were to have, say, or I guess maximize the minimum of M1 and M2. I think that is the actual thing. So basically it is saying that I can have a line over here, but I will have an M2 that is much smaller, so it is much closer to the decision boundary, which means that I can basically get a point that is a circle over here, and even though it is much closer to the I can get an X over here, and even though it is much closer to the rest of the X's, since it is above this line, it will get classified as a circle, right? So the horrific drawing aside, the basic idea is that it wants to maximize a certain margin, and that allows it to generalize well. And we run into a problem when we have data that is either not separable linearly or just more than 2 dimensions. And the solution for that is basically to use a hyperplane, right? When we have data that is not separable linearly, in the instance of these red dots and these blue dots, I basically use a polynomial kernel, which means I increase the dimensionality of this space to something that is greater than 2, and then I create a plane that is in higher dimensions to basically split this data. And now, even though I technically just have a line in higher dimensions, it is allowing me to create this decision boundary that is circular in nature, so it's non-linear, right? And the interesting intuition behind this kind of gets passed on to most of deep neural networks as well, in the sense that we basically, in creating deep neural classifiers, are basically just creating a kernel where, or a backbone that functions as a kernel that works to sort of linearly separate data that is not linearly separable, and then we learn a final linear classifier at the very end, which is basically the final thing, or the hyperplane that gives us the decision of, hey, is this a dog or a cat, is this a red dot or a blue dot. And the connection to this is pretty important because basically if we're I guess lazy as developers, right? If we're just trying to build a solution for a particular pre-built data set, we will probably just integrate a polynomial or an RBF kernel. The idea is that we basically just try to increase the number of dimensions slowly until we get to a point of a marginal return, and then we stop, we say this is my optimal number of parameters or the optimal number of terms, and this degree of separation is best, right? And if we go too far, we're overfitting, so we just kind of find this sort of middle ground. The reason I'm sort of bringing this up is because a deep neural network is in a sense the laziest kernel of all, with a huge advantage that it has an inductive bias. So we can apply certain biases to how these functions work or how these networks behave just by the nature of their architecture. And second, they can also take much more complex inputs, so you don't only need to have this two-dimensional input, you can have images that are much more complex and it can handle it as well. But the fundamental behavior that it is trying to do, as we will see, is very consistent. Sweet. Do you have questions about this at all? I think it makes sense. Alright. Yes,
so when you say that you're able to introduce some like make the STM non-linear, is there any way that can be applied to like k-means clustering? Because it sounds pretty similar, like the approach.
Absolutely, absolutely. So in fact, one of the things that we will be discussing today is a connection to k-means clustering with the principle of deep neural collapse. So you can technically have, like, just strictly speaking, right? You can use a kernel to make a 2D input into a higher dimensional input, and then say I want to find the k nearest neighbors of this point. The kernel, I think, fundamentally is trying to measure similarity between 2 points in higher dimensions, because the kernel function is basically like we have point x and then x prime, and it gives you a sort of a real numbered metric that tells you how close the 2 points are. This could be basically considered like a norm. You can use a L2 norm as a replacement for a kernel, and that would basically give you kn, where you find the k smallest norms, and those k smallest norms will be basically your voters for the final classification. Sweet. One more question.
What's an RBF kernel?
It's a radial basis function. Thank you.
Squared exponential.
Right.
Okay, that makes sense.
It's cool because you can't actually, I think, correct me if I'm wrong, you can't actually compute the higher dimensional quantity of RBF, right? Like, you can't project RBF, like inputs from RBF into higher dimensions, correct?
Inputs from RBF?
Yeah, because the RBF function is infinite. You won't find it in closed form.
No, you will.
Oh.
Because with the RBF you get multiple outputs.
Okay.
It just like kind of measures the covariance between 2 points, x and x prime. Supply those 2 points and it comes up with the covariance.
Oh, I guess the kernel will give you a real value. But if you were to project it with the radial basis function, not the kernel, even then we can get something in real.
Yeah.
Okay. All right.
The squared exponential, the RBF kernel is the best kernel for doing anything because you have analytical solutions for that.
Oh.
Any other kernel, you run into problems of not hitting a closed form solution.
That's interesting. TIL. I should probably check that out. But yeah, sweet. Anyways, that's discussion aside. The first primer is think about these deep neural networks as just very complicated kernels for SVMs. The next thing that we will constrain our study to really is the classifiers. So we will be basically just talking about the classification task. This includes things like transformers because LLMs fundamentally classify what the next word is and just sample it out aggressively. This works for image classifiers, which is what mainly we will be talking about, but it doesn't cost us any generality. This basically works one-to-one for the text-based classifiers as well. I have a question?
What do you mean by auto-aggressively?
Auto-aggressively is I have a model. Let's just assume like this is a black box that takes in the input. I will say today is, and I will give this as an input. The model predicts today is Thursday, and then you feed this back into this input, and you have today is Thursday, and then it will respond with the next prediction as I don't know, sir. All right, so something basically, and it's basically this is a cyclic prediction where I will add today is Thursday, sir, and then I will make that this input, and then I will ask for another output from there. Okay. So without loss of generality, we are constraining our study to image classifiers, but this works pretty generally. We will see in one of the papers actually even results from transformers, so that's cool. But that is one thing. The other thing is the traditional sort of paradigm that we face in machine learning is I have more data points than I have parameters, and you have to basically find some generalized explanation of this data in order for this model to basically generalize, right? The way we can quantify learning is by saying that I have a lot of data that is very, very complicated, but I have a simple explanation for this. And that simple explanation fundamentally is what we want to obtain with machine learning. But very, very recently we have been running into different issues where we have over-parameterized learning, wherein you have more parameters than your data points. And now logically this doesn't make any sense because I have effectively a database or a system that can learn information or memorize information rather than learn the fundamental concepts that underlie it. And logically this does not make any sense. It doesn't make any sense for this setup to work, because if I were to take like a simple example of a linear classifier, I have a line, I have 2 points, right, and I have the definition of this as mx plus b. I can basically set any 2 points over here on the 2D plane. I am going to be able to draw a line between them, right? It is not telling me anything about this data because I can't reasonably interpolate between this line, and I can sort of convince myself by saying that, oh dude, this is so off. I can't really convince myself by saying that there is some real intrinsic conceptual meaning that underlies it. And we basically face this exact same situation, but for these bigger, deeper neural networks, where it has enough information to, or like it has enough parameters to basically memorize everything. However, in practice, we see that this does not happen. And the DNC, or deep neural collapse, actually explains some of that, along with another theory which maybe we will get into if we have the time. So the big question is, why does over-parameterized learning generalize at all? Why does it basically take on the correct representation and in fact performs better than the traditional setting where we have fewer parameters? So that is something that is interesting to think about, and maybe we get some time to like semi-satisfiably answer that question. So that was just some general background. Does everyone follow so far? Any questions for me at this point? Alright, sweet. So deep neural collapse, let's sort of jump right into the thick of it. It is a phenomenon that describes the rigidity in the feature representations of overtrained deep neural networks. So we took the deep neural network paradigm or the setup that we have from over here. Just imagine we have some convolutional neural network with as our backbone a MLP that does perform some form of classification, and we get our final result at the end. So if basically what these researchers found was that there is an incredible degree of rigidity in the feature representations of the final layers of deep neural networks if you basically train them beyond a certain point. So now there are two things that are semi-confusing. The first is rigidity. How do you define rigidity in a sort of quantifiable way? And overtrained. So we will first talk about overtrained. Overtrained basically means that when you have a sufficiently expressive network, right? So we have sufficiently expressive network basically just means overparameterized, such that it can minimize the loss and such that it basically satisfies a zero training error, wherein you have your entire training set that is effectively memorized. However, you still have a non-zero error. So you can theoretically improve, but if you just take the argmax, it will basically say that this is a perfect prediction. This point, the point at which you get zero training error but not zero training loss, is called the terminal point of training. If you just continue to train it beyond that point, you basically have a model that is overtrained. The rigidity is the next thing that we are going to be talking about. We quantify rigidity by 4 key metrics, which, if and only if satisfied, implies DNC or deep neural collapse. Any question?
I didn't understand what train means.
Right.
Are we saying it is for test accuracy?
Right. Okay. So for now, we are only really talking about training accuracy, right? Let's assume we have let me try to think of a accuracy or like a loss curve that sounds correct. Okay, so alright, here we have 2 curves, right? One is my training curve and one is my accuracy curve. So accuracy over here, and then I have training over here. Oh shoot, that is so wrong. These are y-axes. Training, and then accuracy, and these are both for train. Right, and this is the number of iterations or just time. Same thing for the one above. Right, so the idea is that I have a model that is over-parameterized, which means that it can theoretically memorize every single data point that is present within the training set. We start learning, and we basically at some point get to a stage where we have 100% training accuracy. So this is 100%, right? And we have basically reached over here is where we basically touch the 100% accuracy mark. And for training loss, we have something that is similar but not exactly the same. So we have this sort of setup where we're going down the loss, and we are still reducing our loss consistently. However, we have a non-zero loss. So as an example of a logit, we can have the target class be 0 and 1, and we can have the logits be, or let's say the softmax activated logits be 0.4 and 0.6, right? So now if I were to extract the actual prediction, the argmax of this, it will tell me that the predicted class is class 1, right? Class 0 and class 1. And this will also tell me the predicted class is class 1. So I don't have any training error over here. So this is equal to this. This holds true, right? Or actually this is 0 because I'm trying to look at error. So I don't have any training error for my entire data set. Now is it in focus? Not really. Okay, so I have the training loss that is basically training error that is basically 0. However, my actual loss is not 0, because if I were to compute cross entropy wants this to be exactly it wants it to be exactly 0, 1, right? So it's not satisfied yet, even though our training error is satisfied. So the idea is basically once you cross a point where you have no training error, but you have some degree of training loss, you are overtraining your model. Right, sweet. Do we have any other additional questions? Alright, cool. So yeah, this is terminal point of training, or TPT. Right, once we train it beyond this point, the model is overtrained. What does rigidity mean? Rigidity is quantified by 4 key metrics, which if and only if satisfied implies D and C. We also use these sort of metrics to learn certain behaviors or characteristics of these deep neural classifiers. What exactly are the 4 key metrics is, I guess, the next obvious question, which is exactly what we're going to discuss now. So the first one is the collapse of variability. So at a high level, right, this is the evolution of the penultimate layer outputs of a VGG13 model trained on the Cypher 10 dataset. This is basically just the final, or the penultimate layer and its outputs, right? So if it has an output in R of 3, this is basically a visualization for that. If it is in R of greater than 3, this visualization does not work, but it's basically 3 components of it. You can look at it that way. So basically, what the penultimate layer is doing is that, or what the model up to the penultimate layer is doing, is it is sort of learning this setup. And this is what you get basically after you overtrain all the way to your training loss being 0. So if this ends up being 0, is where you basically will see this kind of a setup, where all of the points are sort of clustered towards these 3 central regions. And these 3 central regions all represent 3 different classes. So if I have cat, dog and mouse are those 3 kind of spokes. And in the starting of training or towards the middle part of training, we see a lot of variance around these spokes, right? This in the start basically seems mostly random, but as training progresses, we are able to see that variance reduces quite significantly.
So
Yes.
Is the argument here that, like, instead of the penultimate layer, it should be the final layer, which collapses to a basis for, like, R3, for example?
So the final layer is basically what converts the final output, like the final output feature vector, to the final classification. The penultimate layer is trying to make the input linearly separable. So going back to the kernel trick example, right?
Yeah.
We have all of the layers from the start of the neural network up to the penultimate layer functioning as a kernel, where it wants to basically transform your input from whatever dimensionality it is into something in a higher dimensional space. So it can be 3, it can be 4, it can be 500, but you basically will use that R in 500 to train a linear classifier at the very end, which is basically a hyperplane that determines the classification for each. So the penultimate layer, at this stage we are not trying to influence the behavior, we are just trying to observe what is happening, and this is just what we observe. So
I still don't understand. So this
Right.
is more trying to, like, not extract features, but, like, understand the layers before it so that we can eventually slice it through with the hyperplane.
yes,
But how come making all these vectors more orthogonal is a bad thing?
oh, it's not a bad thing.
Oh.
It's actually a good thing.
Oh, okay.
Yeah. So the increasing the degree of separation actually improves the generalization
Okay,
performance, and is part of the reason why it works, why over-parameterized training works. So it definitely is a good thing.
Okay, I was just confused because it said collapses and it sounded sort of negative.
Oh, no, it's just saying the variance is collapsing, which means that the variance goes from very high to very low, that's all. Okay, sweet. Good questions, though. Thank you. Any more questions? Yes.
What was feature representation? You said that was part of the definition for fluency.
Right. Feature representation is basically if I have a feed-forward neural network like this that is kind of just going through the layers, I'm basically forward propagating from my input, which is basically the image. I won't worry about dimensions too much, but you're basically sort of forward propagating from the input layer all the way to your output layer. The output layer is the total number of classes that you have at the very end, and you basically define whatever the dimensions are for these latent vectors, and that output of the latent vector is the feature representation. So for the case of convolutional neural networks, the structure is going to be the number of channels times the dimension of the feature map, which is D1 times D2. If I can go back, maybe it may look a little bit clearer. So the output over here that you get basically before this new transformation is the feature map. Awesome. Sweet. More questions?
In what sense is it like representing the structure? Is that like just like if you have like a penultimate layer with like 3 values, is that what it ends up looking like?
Absolutely, yes. If this thing over here was an R of 3, right, we would visualize it in this way, right? It is 3 dimensions and then also 3 classes, which is part of the reason why we are sort of restricted to this. No, actually in 3 dimensions we should be able to create a simplex. I'll get into it. But yeah, basically this is if I just had this output feature map in 3-dimensional space so that I can plot it in 3-dimensional space, this is what it would look like. Crucially, this is during training. So this is in the middle of training, this is once we are well past the point of overtraining. So, right. Sweet. Okay. So now we get into a little bit of the math part because we have to quantify this as a metric. For all our classes K and all of our data points I in N within a specific class. So we're basically performing a bifurcation where we're saying that I have I elements for each individual class and I have K total data points. So that basically, N data points within a class, K times N total data points and K classes. I have the penultimate feature vector, which is basically this output over here. What happened? Okay. We calculate 2 things. First is a class specific mean and a global mean. So class specific mean is basically just calculating, it is the standard definition of the average, right? We take the penultimate feature vector. I think this should actually be the norm of the feature vector so that we get, no, this is in vector space, this is correct. This is our output feature vector just averaged up. So you sum up all of the feature vectors. So if I have, as an example, 1, 1 and 1, then I have 0, 0, 1, and then I have 0, 0, 0. Then basically I am just going to do 1, 1 and then 2 and then divide all of this by 3. So this is just the final computation that I'm doing. And I am doing this for each of the individual classes. So I will do this for the class of cat, I will do this for the class of dog, I will do this for the class of mouse, and so on and so forth. Right? So I basically get K feature vectors at the end of it, and all of these I get K class means at the end of it, apologize, and all of them are in the same dimension, all of them have the exact same dimensionality as the output of the feature map. Then once I have that, I calculate the global mean, which is basically mu sub g. I have K total classes, so I am just summing over all of these mu sub k that I have obtained. So if I have 3, I will add them up and divide them all by 3, and I will get my mu sub g. So we have the class means and we have the global means, and we are basically going to use a definition of, or our definition of these two in order to specify a metric based on the variance. So far, any questions? Yes.
Is n here the number of layers?
N here is the number of data points for a specific class. So if I have 5 classes, I will have, one more assumption of this setup is that each of the classes are balanced in the sense that each class has 5 cats, 5 dogs, 5 everything, right? So it's basically saying you have 5 data points that belong to a specific class K, and in total you will have K times N. I don't think we discuss we go much further beyond the penultimate and the final layer for our discussion for DNC. But one interesting thing is that this assumption exists right now, but the next thing that we're going to be talking about is average gradient outer product, which does not have this make this assumption. So it's actually marginally better than what we have right now. Okay, so now we're basically going to discuss the actual formulae for the collapse of variability. We are computing the covariance within each of the means with this equation, and that's the W for within, and we compute the covariance between each of the means that we have, so this is covariance between. It is just the definition of the two. We are really just computing the outer product of the difference of each of the class means minus the global mean, class mean minus the global mean, and we get the covariance for the dots that are present over here. So 1 and 2, you are computing covariance between this, and then again covariance between this, and then covariance between this. So combinations of each of them, and you will get a covariance matrix at the end that represents the covariance between those two. And then you also want the covariance within the specific class. So between 2 points over here, what is the covariance? You will compute that for every single combination within my data set, and you will have the second covariance matrix. So covariance equation 3 for within is actually the one for these points in between, the tiny ones, and the larger points is the covariance between. Once I have these two, I basically just compute the trace of the pseudo inverse of the covariance of between, and that gives me my metric for variability collapse. I'll be talking about pseudo inverse in a second. If I actually have time, I don't know how far we are in. Okay, 8:33. Alright, okay. So, pseudo inverses. The inverse of a matrix traditionally is just defined as this, right? I think everyone is comfortable with this, but if not, I can discuss it further. So we just have AB equals BA, and both of them return the identity. In this case, B becomes yes?
Yeah, is there a relationship between the covariance between and covariance within?
We are computing the relation between it. So we are computing the correlation between those two to basically just create a compound metric. However, by default, there is no covariance between.
Or any sort of relationship.
We can compute it. We can compute it, but these two terms separate are. Okay, wait. Let me think about this. So I don't give you misinformation. We have each feature vector and the mean between the feature vector because assuming we have constant this, if we have like a constant center, so the expectation is constant, these two should be invariant to each other because this is fixed and this is a function of all of these, which makes this fixed as well. So if this has a higher variance but the same expectation or the same mean, then it will not affect this one at all. And if the covariance between these two is high, that would mean that we have a high degree of variance between these two. Let me think. Yeah, even this will be invariant, right? So it should not affect they should not affect each other. However, if you want to compute the covariance between between 2 points of different classes, theoretically you can do that. I don't think there should be anything stopping you from evaluating that quantity. But that would probably have to be computed against the global mean as opposed to the specific K mean. Okay, sweet, great question. Okay, so going back to the inverse, we just get our identity back, and in that case we have B is an inverse of A is an inverse of B. But what about the generalized case where we have n cross m, right? We don't have an inverse that is defined for this in all cases because AB is not necessarily equal to BA. And AB equal to BA I don't even think is computable. So in this case we basically use a pseudo-inverse, which is our generalized definition of an inverse that only satisfies a subset of the properties that the inverse does. So the inverse by itself looks very, very simple. If you plug in the definition of the standard inverse, it will satisfy all of these conditions. But they basically want to create a more nuanced definition for in order to be able to use it in a more generalized setting. And you basically are restricted to the use of the pseudo-inverse within these sort of set of operations. So the basic idea is that realistically only treat it like a pseudo-inverse. If you are reading literature, most likely you don't have to worry about the implications of the pseudo-inverse being something completely separate. But if you are working on your own thing, you want to make sure that you can technically compute a pseudo-inverse, and if you compute a pseudo-inverse, all of these properties should hold, and you should not be expecting something that is beyond this set of properties, because in that case you are going to be your system is not going to work basically. So yeah, for reading papers, simple is to just assume that it works and hope and pray that it works. We're reading NeurIPS publication, so I can tell you in good authority that this is correct. But yeah, anyways, X star refers to the conjugate transpose of X. The transpose of real numbers is just the negative of the real number. It's the same thing just with the transpose of a standard matrix. The implication is that now we can compute correlation between general matrix dimensions and don't have to worry about the dimensionality aspect of things. Sweet. Or like require a square matrix. So that was NC1 basically. That was NC1 basically. We're just trying to minimize, or we're not trying to, we're just observing a minimization in the variances within the classes and then also between the classes. So that is NC1. NC2 is the simplex ETF. So we discussed just the variances but not the actual structure of this system. And the structure of the system is sort of orthogonal to each other. I think it's a weak way to say it, but the actual word is equiangular tight frame. And it took me a second to understand this, but I made this connection between the Vesper theory from chemistry. Does anyone remember derived trigger PTSD? I'm sorry. But the general idea is that you have elements or like atoms that are that want to repel each other and try to maximize the distance between each other, and this is similar to basically what is happening in overtraining. So when we get the Nobel Prize in chemistry, it should not come as a surprise. Anyways, the idea behind a simplex equiangular tight frame is actually quite straightforward. It just sounds complicated. A simplex is a simplest polytope, which is an object with flat sides. So it is just a generalization of a triangle. I have a point in one dimension, I have a line in 2 dimensions, I have a triangle in 3 dimensions, I have a polyhedron in 4 dimensions, and I lose inspiration beyond that. So the basic idea is just that you are extending this to as many dimensions as the number of classes that you have. and it is trying to maximize the distance between each of these classmates. And it maximizes the distance because we are using the because these individually are normalized, so their final value is 1. The sum, their absolute value or the norm is 1. So it's basically just doing it by maximizing the angle as much as possible. So equiangular tight frame is a matrix M in K cross M. So you can consider you have K M-dimensional matrices such that it satisfies the following property. It's the same geometric structure that we looked at over here, but the idea comes into play when we try to basically quantify, right? We understand geometrically what it means, but we need to find a numeric way of saying that, hey, my structure is now a simplex ETF, or no, it is not yet a simplex ETF, it is quite random in nature. So we basically use this relation in order to set up our deviation from the simplex ETF. A standard simplex ETF has the following structure. This is the matrix of ones, so it's C times C, just 1, 1, 1 everywhere, divided by C, so it's 1 over C everywhere now, and this is your identity matrix. That whole thing is then multiplied by the root of C over C minus 1.
What is C?
C can be anything, it is just the number of dimensions for the simplex ETF. For our case, I think it will be K, but let me confirm before saying that. Yeah, it is K. So K is in this case our number of classes. So C can be anything because I'm introducing sort of the general definition of simplex ETF. So generally simplex ETF is a matrix with this sort of a shape.
Wait, am I getting this wrong? Or would this be, I know like the picture is oversimplifying it, but would this be related to like saying how close are these vectors to an orthogonal basis? Or
Yes. It's basically just trying to maximize the angle. In this case, we would get the orthogonal basis, but I think if you try to increase the number of classes, right, and don't increase the number of the dimensions of space that you are projecting into, you will not get 90 degrees exactly.
Right.
You might get something that is a little bit lesser, and if you have only 2 classes, you will get a spoke which is just 180, right? So it's the idea is just maximize the angle wherever possible, and that structure can be quantified mathematically quite neatly using the simplex ETF.
Okay, got it.
Okay, sweet. Do you have more questions?
Why are we doing this again?
So the idea is that we are trying to observe behavior in training, right? So there are sort of phases of training that we are trying to observe certain empirical metrics against, and we just want a way to numerically quantify this geometric behavior that we are seeing, where we quantified the first thing where the variability between each of these individual points are collapsing. The second thing is we want to quantify the fact that these points sort of create this equiangular structure, and we sort of have to devise a clever way of saying that this is numerically how I state, this is numerically how it is possible for me to state that I am this close to the structure of a simplex ETF or this far away from a structure of a simplex ETF. Because it's kind of like a loss function where it is minimizing the loss without me directly optimizing for it, but I need to know how far I am to my correct prediction. So I want to know how far I am to a real simplex ETF or how far I am to the collapsing of the variability. Does that help?
So you get a matrix, but how does that matrix help you quantify that?
Oh, we get to that in the next slide. Right away. Right. Awesome. Cool. You're running ahead of me. That is always good. Sweet. So we can use this to define NC2, which is our second metric. Given the recenter class means that we have from here, they are equidistant if we just have the fact that the distance is the same. The 2 norm is the same for every single combination of K in my set of classes. And we can then sort of normalize each feature vector. Okay, also high level, right? equations 13 and 14 are trying to basically create the structure of the simplex ETF using the feature vector. So we basically defined a simplex ETF before, but now we have this sort of feature space that is sort of here, and we want to basically try to say how close is this thing to an ETF. So we have to convert it into a form factor that we can like directly compare it to the ETF that we have defined. So that's basically the procedure that we are defining over here, where we concatenate all of the class features that we have, or the normalized, we concatenate all of the normalized class features that we have. So we are normalizing within the specific class and concatenating it to this big K by M matrix, and M is now compared to the distance from the actual simplex ETF. So this M is basically what we get over here, and this simplex ETF is the definition that we had in the previous slide. So equation number 12. So it is, I think, slightly different. It is C over K minus 1. That is because we want to integrate a second condition, which is the fact that these two also have to be was it over here? This term over here, where the inner product or the absolute value of the inner product between these two is consistent. So it is exactly the same because they are equidistant. So we have this equidistant and equiangular. This is equidistant. It is not equiangular. No. This is cosine similarity. This is equiangular and this is tight, basically meaning that you cannot increase it at all, and equiangular means that it is equal angles. So we have to satisfy both of these definitions. I realized I glossed over the first one, but yeah, and we can satisfy both of these definitions by basically creating the minor change to this C over here, the square root of C term that is there on top, it just goes away. So we have the concatenated feature space, which is one thing that we have obtained from our model output, and we have the definition of the simplex ETF. We basically just calculate the normed difference of this and say this is my NC2 metric. So F sub F over here just means Frobenius norm. That's just I think mathematicians like to make simple things complicated. If I am calculating this minus or like the normed of this, right? This is just the equivalent of me computing of me first flattening this into 0, 0, 1, 1 minus 1, 1, 1, 1, and then computing the norm over here. So the 2 norm over here. So it's just a flattening step that is applied before we compute the before we get our real valued output. So we have that the feature vector that we basically structured into the simplex form. We have our canonical simplex and say how close are you to my actual number, and if it's close to 0, that means it's good. If it's far from 0, that means we have not gotten to that point yet, and that sets up our second metric. So it's 8:50. And I was supposed to be done to slide like 20 at this point, I guess. So we'll talk about deep neural collapse today, and then the next week, or probably next week, we'll have to figure out the rescheduling stuff. We'll cover the AGOP and how it is induced, and I'm sorry about that. But yeah, I don't want to keep you out here for another hour. Anyways, NC3 is self-dual alignment. So this is basically us sort of going one step further, where we're saying now I want to look at the final layer and the symmetry between the final layer to the penultimate layer, and it basically says that the final layer's weights aligns with the simplex ETF of M. So we got the simplex ETF of M previously, and if we just compute M over the Frobenius norm, so just normalizing it again, times A, which is supposed to be W, sorry about that, we basically say that this is proportional to the simplex ETF. So it itself is imbibing the structure of the simplex EDF as part of training. And it uses that specific structure to basically promote the logic values of the final classification and basically give you the final prediction. So this one is relatively similar, where I am computing the outer product, which is cosine similarity, normalizing that between A and M, or W and M. So you can assume this W is actually an A over here, and then also just subtracting that with the canonical simplex. So I'm saying that I have the output structure of my penultimate layer, I have the weights of my final layer, and I am basically calculating the correlation between these two things. And if they are highly correlated, you would not expect that to change at all. And since it imbibes the structure of a simplex EDF, we're basically saying that this is a simplex EDF, and this entire value ends up being close to 0. Sweet. Alright, the fourth and the final property, right, which I think goes back to some point that was mentioned about KNN, was that for a test data point, the classification result is effectively equal to the KNN rule. So if we recall from the bit over here, we can see that if I basically sort of add a point over here, I can tell that the neighbor that's closest to it, to me, is this point. Therefore, I will simply classify my new input as the class that basically is imbibed by this ball over here. And there is a relatively straightforward way to encode that, where we take the class mean that has the lowest distance to the output feature vector of, or the penultimate feature output of my new test data point, and we can compare that this in fact does hold by just computing the mean of the incorrect predictions. So this entire thing goes over here and gives me the final predicted class. Argmax of yi is just the final logic that I compute argmax to get whatever the predicted class is. And if you basically reach the point of overtraining, this is 0. So that is our NC4 metric. So if each of the 4 previous metrics tends towards 0, the network is considered collapsed, and we get a deep neural, experience the phenomenon of deep neural collapse. Now, the implications of this are quite severe. So one very interesting property about deep neural collapse is the fact that it has data independence, right? And what that means is it doesn't really care about the inherent data distribution that it is learning. This is a property of the fact that it is over-parameterized, right? Which means that we take cipher 10 and give it random labels. We basically just guess whatever. It doesn't have to mean anything. And it is able to reduce the error rate very easily. So for width equals 4, it kind of fails, but like everywhere else, it's super happy, right? Yes.
Wait, just to clarify, what is width here?
Width is so the this size over here basically becomes the width.
Oh, okay.
So the number of channels was either 4, 8, 16, 32, or 64.
So it's like size of the intermediate representation.
Yeah, size of the intermediate representation. Absolutely. So we evaluate against NC 1 through 3, and we can see that we are basically getting the very, very low scores for each of our metrics. So we are able to, this actually seems, log scale, that makes sense. I was confused because this is below 0 and norms are never below 0, but no, it's fine. Anyways, we have NC1, NC2, NC3 over here, and we can see that we are reaching the point of deep neural collapse because we have all of these values that are effectively approaching 0, right? So do we really want this system? Do we want this phenomenon? Should we go back to our original setup? The answer is we do want this, so do not go back to your original setup. One of the reasons why is that out of distribution inference becomes significantly easier, because if we have a setup where any point within my training distribution goes as close as possible to a target point if I have a distance in a test point that is significantly high. Even if the prediction is correct, that is basically telling me that it is likely to be out of my training distribution because it is not able, because the kernel that we've learned is not able to basically put its spot onto the target point, or like to the target point, which is the class mean. So the class mean almost sort of represents the classification, but it gives you some more detail back because it gives you almost the model's true confidence in terms of how close it is to being within the training distribution. The second one is we can just force a simplex. So overtraining is not something that we necessarily need to do. We know that this structure leads to performance improvements because we have seen like the double descent. This is in part because of overtraining, and the very simple sort of ablation that we can do to the neural network architecture is we can say that, hey, I know you like the fact that the simplex, or like, I know that you work well in the simplex ETF setting, so instead of letting you learn that, I will just fix that for you, and you have to learn a simplex ETF as opposed to the original set of classification targets that you have. This line did not render correctly, but I will fix that for next time. Yeah, that is deep neural collapse. If I knew that we were going to end on this, I would probably have spoken or like added another slide about why it is super awesome. But at a high level, I will end by just talking about why this setup works in the first place. At the very high level. There was a study that was conducted for the complexity of a monkey randomly typing and getting the first 100 digits of pi, right? That is just 1 to the 10 raised to the power of 100 and plus 1, and that's like the likelihood of it getting pi to 100 digits correct at random, right? Now, the interesting thing that we can sort of do to ablate this study is constrain our input, or like the input where the monkey is typing, and instead of saying, hey, instead of predicting the first 100 digits of pi, or like instead of typing out the first 100 digits of pi, how likely is it for a monkey to type out code that basically prints out the first 100 digits of pi? And the shortest C code that prints out 100 digits of pi is smaller than the first 100 digits of pi, right? So it's smaller than 100 digits, which means that if you were to put the same monkey, instead of telling him to work on Notepad, if you told him to work on the C compiler or Vim and told him to auto-compile this code, you would have a higher chance of him basically getting the first 100 digits of pi than if he just typed it out on a Notepad, right? And this is something that's very interesting, wherein the structure of the neural networks that we use imbibe in themselves this tenacity to basically give a simple explanation back outside, and a consequence of that is that it sort of has its own inductive bias to find the simplest solution to the problem, even though it can memorize everything. And that is part of the reason why it is able to generalize so well, because you give it an incredible amount of power, and it has an inductive bias. So if you were to basically just randomly sample a set of weights, it is much more likely to give you a simple function at the output, as opposed to just uniformly sampling all of the functions that it can represent. And that is part of the reason why double descent and over-parameterized training works so well. Next week we will talk about AGOP and how we can break the data independence assumption and get a representation for deep neural collapse that gives us even more power with respect to our fusion learning. So thank you all for coming. Have a great rest of your week, and I'll see you all soon.